So what we're going to talk about now is collective communications, and these are quite important. I've mentioned them a few times. In fact, I mean, it might seem strange that the example we've used for the first exercise, which is the pi example, and also the second example, adding data up by a ring around a ring, are both examples which should really be done using non-blocking communications. But I've thought about this, but actually they're both extremely useful examples. The pi example for illustrating point-to-point communication, and the message round a ring example for illustrating non-blocking communication. And one of the good things is, having implemented them by hand, if you put timing in, you would be able to implement them using a reduction operation and actually see how much faster the reduction operations are. And that's one of the exercises actually in the sheet. So collective communication is communication involving a group of processes. Quite importantly, what we've done so far has actually been a pair of processes. One process calls a send, the other process calls a receive. But actually, what we're really actually trying to achieve in a lot of these examples is a collective communication between all the processes. And MPI has those built in as an option. So the examples of barrier synchronization, which we don't often use, but if you look at the exercise sheet, one of the main uses for barrier is if you're doing timing. It's quite a complicated question of how long does an MPI program take, because all the processes are running individually. So if you're going to do a timing, it's actually quite useful to call a barrier, which synchronizes them in time, start the clock, and then call a barrier and end the clock. And that gives you a sort of a maximum time for all the processes. But the ones which are actually useful in real programs are broadcast, scatter, and gather, which are often used at the start of a program. Broadcast some data out, scatter some data out, gather at the end. But the critical performance critical operations for almost all scientific and technical programs are global sums, or possibly global maxims, but actually global sums. You know, that's often what you've done. You've taken a calculation, like the pi calculation, you've distributed it up across processes. Each process knows a sub-value, and in a real calculation, it might be you split up the United Kingdom into square blocks to simulate the weather. So each process is simulating the weather over a rectangular region of the United Kingdom. The rainfall over a random rectangular region of the United Kingdom is a meaningless number. But what is meaningful is the total rainfall over the UK, which is the sum of all these private numbers. So reduction operations, and particularly MPI sum, are at the core of an awful lot of parallel scientific and technical programming algorithms. So the characteristics are, it's a collective action over communicator. So it's collective over communicator. If we pass MPI common world, as we will be in these exercises, it's collective over all the processes, obviously. But you can subdivide. So if you wanted to do the sum of a value over all the even processes, or all over all the odd processes, you would have to create a subcommunicator which has included the even processes or the odd processes. But we'll just think of common world at the moment. All processes must communicate. Synchronization may or may not occur. It's a bit of a technicality, but in my mind, the most useful model for collective communication is that there is synchronization. So imagine in your mind that they start off doing, the collective communication itself starts off doing a barrier, does its work, does a barrier, then returns to you. Now, there may be ways to optimize around that, but that's the most useful way of thinking about it. All processes have to call the collective call. Okay, that's really, really important. Standard collective operations are blocking. Now, there are non-blocking versions which were introduced, non-blocking versions which were introduced into on the MPI 3 level, but they're not, they're an obvious extension. Instead of calling a reduction operation, you call a non-blocking reduction operation, you get a handle back a request, and you can wait later on for that to complete. In practice, they're rarely of any use. We can discuss that later, but I'm just going to talk about the blocking versions here, but the non-blocking versions are a trivial extension syntactically. There are no tags because all the processes are communicating, so you don't need to have tags. You know they're all taking place. The receive buffers must be exactly the right size. Okay, so you know, there are send and receive buffers. If you're doing a global sum, the send buffer is your input value, the receive buffer is the return value. MPI will not check that these values are, that your buffers are the right size. It just it's up to you. MPI could check, there's no reason why it couldn't, but they've decided not to. So why do you think MPI doesn't check? You know, you're calling a reduction operation on Archer 2, you're calling a reduction operation across 100,000 processes, it's going to add all these numbers together. Why don't you supply buffer sizes and MPI checks that they're all correct? Why would that not be something you'd want it to do? It would make the program more robust and easier to debug. Time, yes. So merely to check that all the buffers are the right size, it would take an enormous amount of time. It's got 100,000 processes giving it buffer size. It has to go and say, is yours, are you, it would obviate the entire reason for collective communications, which are to be fast. Okay, they have to be implemented efficiently. They're such at the core of scientific and technical algorithms. They have to be implemented efficiently. So here is where ease of use and robustness is sacrificed for speed. So a barrier synchronization is a barrier. You pass a communicator, all the processes in that communicator synchronize, and they won't leave the barrier until they've all entered. And I said we could discuss later on. I mean, it's a subtle point, but you almost never need barriers in MPI code. 99% of the time you see a barrier in an MPI code, it's because the person doesn't understand what they're doing, the author of the code. You almost never need barriers to have a correct code. Yeah, almost never. You have to write very contrived programs which require barriers for correctness. Now, they can be useful to make, you know, if you're doing timing for everyone to line up, it may give you a cute fuzzy feeling to know all your processes are lined up in time. But if putting in a barrier makes your program correct when it's not correct before, 99.9% sure you've got a bug in your program. It is quite a subtle point, but the send and receive operations themselves, or the collectives themselves, almost always do the synchronization which is required. But the broadcast is actually a useful one. Okay, you've read some data into a buffer, and you want to broadcast it out for everybody. So what on entry, when you so the root here says who has the data. So often root is 0. It doesn't have to be, but you might read some data in from file on rank 0, and you want to copy that data to everybody verbatim. It might be an integer, or it might be a bunch of parameters. So you have a buffer, which is a certain number of data types. This might be 10 integers. And on entry to the broadcast, now everybody has to call the broadcast, okay? All the processes are taking part in the broadcast. So they all have to call it. It happens to be within that side of the broadcast, they play different roles. The root is clearly sending the data, and the non-root processes are clearly receiving the data. But they all have to call the broadcast. So on entry, the buffer is valid on the root. On exit, the buffer is copied in the same effort. It achieves exactly the same as a point-to-point send of the buffer to all the root process, but it will be done much more efficiently. So I'm going to illustrate scatter, but just before if we did so the root process here is 1, rank 0, 1, 2, 3, 4. If we did imagine these are integers. If we did a broadcast of 5 integers, okay, then what that would do is it would take the 5 integers, and we specified root equals 1. It would take the 5 integers A, B, C, D, E on rank 1 and copy them everywhere. We'd have to have a buffer of a receive buffer of size 5 on every root, on every other process. So if you did a broadcast with count equals 5 of A, B, C, D, E, then every process would get a complete copy of the entire array. And sometimes we want to do that, but sometimes we don't. So imagine this were the traffic model. The root process has read in the entire road from file, and it wants to scatter it into small pieces across all the other processes. You don't want to broadcast it, you want to scatter. You want each process to get a subset of the data, not the whole data, so you want to do a scatter. That's what scatter achieves. Scatter achieves taking an array, a large array, on one root process, here rank 1, and splitting it up into small pieces which are distributed to all the other processes. That's the pattern. So the prototype is you have a send buffer, a send count, and a send type. So that in this case, the send buffer would be the ABCD array, and it would be, say, integers. You have a receive buffer, a receive count, and a receive type. Again, this has to be be able to receive the incoming data, and the root process, on entry, the root process holds valid data, and on exit, all the receive buffers are initialized. So it's important to note that if you look at this diagram, I've only drawn the send buffer, which is this array, as being initialized on the root process here, root rank 1. The send buffer only needs to exist on the root. You don't even need to allocate it on the other ones, okay? So you don't need to, the receive buffer has to exist everywhere, but only the send buffer needs to exist. So yes, deterministic in what sense? So it scatters them in rank order. So the first part goes to the first rank, the second part, is that what you mean? Yeah, yes. So we have a send count, a send buffer, a send count, and a send type, or a buffer receive count and a receive type on a root. So for this example here, the send buffer is this thing, the receive buffer is this thing, these things here. The root is 1. The send type and receive type might be both MPI int or MPI integer. What do you think the send count and receive count are here to achieve this distribution? We start off with an array of size 5, and we end up with an array of size 1 on each process. What do you think send count and receive? It's not obvious. What do you think send count and receive count are? Anyone take a guess? Yes. So you'd think scatter would be. Oh well, no. I'm sending scatter 1 and receive. So most people would say that the send count would be 5 and the receive count would be 1, because this is what you're starting off with, and this is what you're ending up with, these ones down here. Actually, it's not. Both send count and receive count are 1. What you are specifying is the size of the small message, okay? So actually, nowhere in the prototype for this function do you specify the size of the send buffer. You specify the send count and the receive count, which is the size of the data which is sent to each process. But the fact that it reads, in this case, send type and receive type would be MPI int or MPI integer. Send count and receive count would be 1. So how does it know to read off 5 items? Because you're not actually specifying that explicitly in the scatter call. Where does this 5 come from in this example? Exactly, because there are 5 processes. Because there are 5 processes in this communicator. Now you might ask, well, if the count and receive count are both 1 and send type and receive type are both MPI integer, why do I have to specify them both? Isn't that, well, actually, when we come to derived data types, you will see that for if you're a sophisticated, send type and receive type don't need to be the same. But if send type and receive type, in 99.9% of cases in common usage, when send type and receive type are basic data types, not the derived types which we haven't covered yet, then send count and receive count are the same, and the send type and receive type are the same. But you can use it in a more sophisticated way. Gather is just the opposite of scatter, again, except that the input is this guy, sorry, A, B, C, D, E, and the output is this guy, okay? So again, here, the root is the person who gets the data. So gather is, the send buffer here is the small thing, the receive buffer is the big thing. But again, send count and receive count are 1 here. It's the size of each individual message, not anything to do with the total size of the array, okay? So gather and scatter can be useful at broadcast, gather and scatter can be useful at program startup and completion, but actually they're not that critical to performance normally. It's reduction operations, which you do all the time. They're used to compute a result involving data distributed over a group of processes. You do a global sum or product, maximum or minimum, or you can actually do a user-defined operation. And to be honest, global sum is the one which is used almost all the time, okay? Global product is almost never used, because if you take 1,000 numbers and multiply them together, you'll either get 0 or infinity, or big. So I mean, max or min can be useful. You might want to know not just the average age of the class, but who's the oldest or youngest person. You might want to know not just what the average rainfall is in the UK, but what is the maximum or minimum. So in the scatter, the send buffer So in a scatter, the send buffer is A1 to 5, and the receive buffer is A1. Yep, that's correct. But the send count is 1 because it's telling you how much you send to each target process, not the size of the input. Does that help? Yes. Oh, sorry. Oh, well, it depends what you mean. You just pass A or A1 to 5. You could probably pass A1 and Fortran being Fortran, it all works out. And you just pass. I mean, you should pass A or A1 to 5. If you're old-fashioned, you might just pass A1 and cross your fingers. Because of the way Fortran works. But yes, it's A. It's A is just the array. Yeah. So global reduction operations. Well, you could just pass the address of. You could just do, what I could do. Let's do an example. Maybe I should have. You could just do. Let's just sure we have the. Let's. No, that's not what I want. What you could do is can you see my, yeah, okay, stacking. You could do, if you see, you could do int send of 5, int receive, you can't spell, and you could do MPI scatter of send buff, send count, send type, receive buff, and you specify address of receive count, receive type, root, com, something like that. Does that make sense? So that's, you could do that. But if you did 2, if you wanted to do 2 to each, you'd have to do int send 10. You do that. You do that. Say. So what if send has 6 elements and you scatter to 5? Well, that's fine. It just keeps reading. Yeah. I could do int send of. Does that make sense? Because it just sends, sends the first 2 to the first process, the next 2 to the next process, the next to the next process, and when it gets to the final process, it stops. I thought you were going to ask whether the send has 5 elements and you scatter to 6. In that case, it reads off the end, and you get garbage probably, because MPI doesn't check. Does that answer your question? Yeah. So so there are predefined. Oh, I'm not sharing my slide. There are, I was at this slide, there are predefined reduction operations. So you can do a max, min, sum product. You can do logical and bitwise and, logical or and bitwise or, logical exclusive or and bitwise exclusive or. You can also actually, the max and min are often not that useful because you might say, what's the maximum rainfall in the UK? 10 inches, whatever that is, 25 centimeters. you might want to say, well, where was that? So max lock and min lock actually give you not just the maximum min value, but which process had that maximum min value, which is often a bit more useful. And the logical and logical OR can actually be useful for error checking. So basically, if you want to do a global error check, you can basically, everyone sets a flag 1 or 0, okay? And if 1 means everything's okay and 0 means there's a problem, you can do a logical AND. So you do AND. So if anybody specifies a 0, which means there's a problem, then you get the 0 back out. So I have used logical AND or logical OR as a way of doing a global error test. Everyone has their own error flag, and you want to check if any of them is. You could also add them up, but I mean, it's up to you. But MPI sum is the one which is used all the time. So the syntax is MPI reduced. You've got a send buff, a receive buff, a count, a data type, an operation. So MPI op, that's one of these operations, which can be MPI max, MPI min, MPI sum. You have a root, and the answer is placed on the root. So for example, in the pi example, the root was the controller process rank 0, and it's all done within the communicator. So I've got an example here. People get confused about count. This diagram isn't particularly good in that case because here we're running on 4 processes, okay? So what we call an MPI reduce with root equals 1. So so each process is specifying an array of 4 elements, A, B, C, D, E, E, F, G, H, I, J, K, L, M, N, O, P as the send buffer, okay? Because root is 1, the answer, the sum is only placed on rank 1. There is a way of doing it globally, but this is reduced. And it's a bad diagram because the count is 4 and also there are 4 ranks. But the count equals 4 means that you have 4 entries, okay, and you want them individually to be reduced. So the first element is added up over all the processes. The second element is added up over all the processes. The third element is added up over all the processes. And so A circle, E circle, I circle. Now circle means a generic operation, but think of it being addition. So A plus E plus I plus M is put into the first element of the receive buffer of the root process. So the fact is, count is not the number of processes, okay? The number of processes is implicit. It's done across all the processes in the communicator. Count is how many reductions you want to do. And so a single reduction operation with count equals 4 is functionally equivalent to 4 reduction operations of count equals 1, okay? But it is much faster to do a single reduction operation of count equals 4. Why do you think that is? Why is it a good idea? Well, no, so okay, vectorized sum, no, because sum of 1 integer takes a quarter of a nanosecond. The sum of 4 integers might take a nanosecond. It's 0 time. No, it's not memory. It's not memory. Think of running on 1,000, 10,000, 100,000 processes. Yes, less communication. So if I ask you to buy 4 pints of milk, you only communicate once. And sending a message of 4 integers takes exactly the same time as sending a message of 1 integer, because the header, the header is much bigger than that. So if I tell you to buy 4 pints of milk from the supermarket, do you get in the car, drive to the supermarket, buy a pint of milk, come back, and then go get in this car, drive to the supermarket, buy the second pint of milk, and come back? No, you don't do 4. You go to the supermarket, you buy 4 pints of milk, and you come home, because the time is dominated by the travel. Here, the time is dominated by the communication to a vast extent, okay? And so the communication dominates everything. So from left to right, this element here is set to A plus E plus I plus M. This element here is set to B plus F plus J plus N. This element here is set to C plus G plus K plus O. Does that make sense? Yeah. And I've got a specific example actually to make it more obvious. But it is, that is one of, that is the analogy. If you want to buy 4 pints of milk, you don't drive to the supermarket 4 times. Of course, that would actually be illegal in the UK at the moment. I mean, I suppose you're supposed to make 1 journey. Anyway, but there you go. So a global reduction, we want to reduce x, which is our partial value of pi, say, and get a result. So we do MPI reduce, and we want the answer to be on rank 0. Okay. So we do MPI reduce. Input is x, the output is the result. It's one integer. We want to add them, so we do MPI sum. We want the answer placed on rank 0, and we do MPI com. Well, this is exactly. I'll come back to that. So this is exactly what what you'd want to do in the pi example, except it would be one MPI double or MPI double precision. Now, Laurent has asked about the order. You don't have any control over the order, so MPI will do it in an efficient way. It will use some tree-based algorithm, for example. So you don't have any. Why would you want control on the order? It's just rounding errors are rounding errors. So, but you can't control the order, no. MPI, but why would you want to control it? Why would you want to have A plus B plus C, not C plus B plus A? They're both wrong. They're both equally wrong. They're both equally right. I'm interested in, I mean, I'm being slightly disingenuous here, but I mean, we got different answers when we wrote our pi example. I don't understand, but yeah, exactly. I mean, you get, floating point arithmetic is not associative, so there is no correct answer. Different implementation of MPI, absolutely correct. Different implementation of MPI will do it in different ways. What is guaranteed is that for the all reduce, where everyone gets the answer. So okay, so there's so there's two questions here. One is, can you control the order? No, but the other one is, if you do it twice, does it do the same order? Now, what Kono has asked here is actually the more critical question. As I understand it, I've asked, MPI does not guarantee that it will use the same order every time. However, in practice, it does use, because it will be used some prescribed for a given number of processes. It will, well, that's a subtle question. Most MPI implementations will give you the same answer if you call a reduction on the same number of processes, because they will use a predefined order, some tree-based algorithm. And if it doesn't, there will normally be some flag you could set in the MPI library, say, please do reductions reproducibly. I have never seen MPI, if I run a reduction operation on the same number of processes with the same inputs, I've never seen an MPI implementation which gives me different answers, ever. But I don't think it's we should look up that. They may have clarified that's clearly a bit of it. But you should never ever do reduction operations by hand. Yeah, so I would assume, a good MPI implementation will give the same answer every time, and I have never seen one which didn't. Okay, but yes, for debugging, I wouldn't worry about it for debugging. So it's a good question. You can actually do user-defined operations. All that's special about these operations, max, min, is they're predefined. Clearly, what MPI does is it has a structure for combining data, and all it does when it gets the two data together, it says, does David want me to add them, subtract them, take the maximum, or whatever? So these are pre-registered, but you can register your own. In fact, it's hard to think of a valid reduction operation which isn't predefined. But however, when you start to do user-defined data types, and you want to use them in a reduction operation, you have to do a user-defined reduction operation, because we'll see later, you could create an MPI type which is a little matrix, for example. A matrix is a good, isn't it? Well, maybe as a good example. If you wanted to add them together and you passed it to a reduction operation, MPI would say, you've passed through something called an MPI matrix. I've never heard of it. So anyway, but it's slightly convoluted, but you can do it. You can basically extend this set of reduction operations to do your own ones, and you have to write. It's a two-stage process. You have to write the reduction operation, which has to have a fixed prototype. It has to take an input vector, an input-output vector, a length, and a data type, and it has to combine them. So then you write a C or Fortran function which does that, and then you register it with MPI. You say, here's a new function I want you to do, and could you register it? It gives you back a new MPI op, which you can then use later on. So I'm not going to go through the details because it's slightly contrived and tricky with prototypes and things, but you can do it, okay? And I have some examples I could show if you were interested, but it is possible to do your own reduction operations. They have to operate like this, and they need to commute, but sorry, they do not need to commute, but they must be associative. So you can actually do, you can do non-commutative operations, but when you register it, you need to tell MPI this doesn't commute, and that means it has to maintain the order, at least in some sense, but they have to be associative, at least mathematically associative, because of course floating point addition isn't associative, but mathematically addition of real numbers is associative, so that's enough. So the reduction operation is something of again, so it's a two-stage process. You write the reduction operation as a C or Fortran function. You then has to have this prototype, it has to operate in this way. Then you register it with MPI, MPI op create, you give it the function, which is a function pointer. You tell it whether it commutes or not. Normally it does commute, but of course matrix multiplication doesn't. And then you get back an MPI op back, which you can then use. Once you've done that, you can use it. It's on an equal footing to the predefined. It's unusual to do this, but I have seen it done. Variants of MPI reduced. Actually, MPI reduced on its own isn't much use. If you reduce the value, well, they're all doing the reduction. I mean, for example, what do you mean by doing the reduction? When you did the pi example, they were all added on the root. When you did the round of the ring, yeah. So it will be a tree-based thing. It will use some. When you did the message round the ring, everyone was adding the numbers. It will do some efficient tree-based algorithm. So the important point is a naive algorithm, such as your pi example, send all the data to a root process, or the message round the ring, all required order p messages on p processes. Okay, it's almost trivial to beat that, and a good implementation, which uses some tree-based or binary hypercube-based algorithm, will take log p messages, and that's a huge even 1,000 processes. You're talking about sending 1,000 messages for the naive implementation versus 10, because 2 to the 10 is 1,000 in the optimized version. Yeah, but this is the reason that MPI reduction operations are taken as a high level, is to give the MPI library or the implementers as much freedom as possible to do the efficient thing. All reduce is actually, now doing a reduction operation isn't much use, because actually if you reduce a value and only one process knows the answer, what can you do with it? You can't take any decision on it. You can't stop or terminate because only one person knows it. All you can really usefully do is print it to the screen. Some people do a reduce then a broadcast. You should never do that. If you want everyone to know the answer, and actually most algorithms you need everyone to know the answer, you do an all reduce. So an all reduce is just like a reduce, except the answer goes everywhere. So it's the same picture here, but the answer goes everywhere. Everybody gets the answer. Okay, it is functionally equivalent to a reduce plus a broadcast, but you should never do reduce plus broadcast. Just do an all reduce. So actually, our pi example was a reduce, where only the root process got the answer. Our message round a ring example is an all reduce, because everyone gets the answer, the same answer. I've got an example here. So it's just like reduce, except it's an all reduce, and you basically don't have a root process. It's the same prototype. So I put an example in. So if we want to reduce a single integer, again, it's exactly the same function called as all reduce, except there's no root. X is the input, results the output. It's one integer. MPI sum across MPI com world. Sum of all the X values is placed in result. The result is only placed there every. So that is a terrible typo. I think I just introduced that just now. I did just introduce that now. Apologies, because this is a new slide. So apologies for that. That's a bad. The result is computed on every processor, okay, or stored on it. The result is stored on every processor, or I should say processor. Ah, sorry. You can tell I did this at short notice. Should never say processor. So it's a bit embarrassing. I'm now having to show you. So these are. So sorry about that. I should say process here, not processor. So I'll go back to the well. So this is okay. Sum of all the x values is placed in result. The result is stored on every process. Okay. Actually, to illustrate the use of an array, imagine you've computed the pressure, temperature, and rainfall into locally. Pressure. Each process is doing you're doing weather forecasting simulation. Each process is responsible for a section of land, and it's computed the pressure, temperature, and rainfall over that at that point. And these are local data. Okay. So if I want to add them all up, I would stick them in a little array. I say local data 1 is pressure, local data 2 is temperature, local data 3 is rainfall. I want to add, so I do MPI or reduce. Local data is the input, global data is the output. There's 3 items: MPI double precision, MPI sum, MPI common mode error. And so what happens is that these values are accumulated across, and then I can print them out. The global PT and R are the global. So apologies for this. You can see that these I wasn't really paying attention when I did. These are new slides because there's a few typos in them. Apologies for that. Or in C, it's just the same. Local data, global data, pressure, temperature, rainfall. You all reduce the local data, and you're doing 3 items, okay? And then you're printing them out. So hopefully that would be functionally equivalent to doing 3 reductions for pressure, temperature, and rainfall, but probably 3 times as fast. Does that make sense? There are some MPI scan is an interesting one. Okay, MPI scan is like MPI sum, except that it stops. So what it means is that the first process in MPI all reduce, these numbers will be set to A plus E plus I plus M, B plus F plus J plus N. In a scan, it stops. So that is set to A. That's A plus E. That's A plus E plus I, and that's A plus E plus I plus M. It's a partial operation. It computes the result on process I is all the inputs from the processes less than I. Okay, and this can be useful sometimes. There are some algorithms where this is useful. So it's like a partial. It's like a partial reduction, but it stops. It doesn't do it over everybody. There's also it's a partial sum. So it's the same. It's exactly the same prototype as MPI or reduce, but the reduction stops. It doesn't go all the way. So each process gets a different answer. The exercise is exercise 5 on the sheet. Rewrite the pass around a ring program to use MPI double reduction. Actually, it's a one-liner, but actually the interesting thing is to compare the time. So I really, this is reduction operations are very important, but to do the reduction, to implement the message around a ring example using reduction operation is one line, MPI or reduce input output. So please, I would recommend you work on the point-to-point non-blocking operation to learn how to use non-blocking communications, which is a really key technique in practical MPI programming. And then if you do have time to do this, move on, but then you want to do the timing, because it's really only the timing which is interesting here. Okay, so is that everything? While we're here, I will also show you what I've done for the Slurm, for Slurm. So I've updated the website. So if you look, I now have an example Slurm script and that's what you need. So you just you submit with sbatch hello.job. This runs MPI. This runs hello on 4 processes. PPN is, this is explained here, PPN is processes per node. So if you want to run on more than one node, you have to set nodes equals 2. This PPN stays as 48. But if you wanted to run it as it's set on 80, for example, for 80 processes, you would set nodes equals 2 up there and use MPI run minus N80 minus PPN 48 hello. Place 48 processes in the first node and the remaining 30 on the second. So, and you just do s batch hello.job. And as you saw when we ran on, I'm updating the crib sheet, but the output appears in a file called slurm 5734.out, or you'll see a file appear which has the screen output in it. But I put that up on the so if you're on the next gen IO system and you want to run in batch to do timings, then you should use this slurm script and edit it as appropriate. So I'll go back to the I'll share the exercise sheet because that's what we're doing. I hope you'll be working on. There is a broadcast and scatter example just to implement them using point to point. It was really there to show you 2 things: A, how to send messages of not a lot of the examples of you simply sending a single integer. This sends a bunch of, but it also shows you how to send, will get you thinking about how to send a subsection of an array. Not just send the whole array, but you don't, when you do a scatter, you want to send the first part of the array to the first process and the second part of the array second. So the send buffer needs to be moved along the array, and I'll illustrate how to do that. But actually, the ping pong exercise, this is the one which is the most communications. So if there are no questions, yeah, it's funny, I suddenly hear my voice every now and again. Very briefly, I got my voice broadcast back to me, which is a bit strange, a bit disconcerting. But so if there aren't any questions, myself and I think it's Queven is on point today. We'll be around till 1. Then there'll be a lunch break till 2. I hope you'll have a nice lunch. I might have my lunch outside. The weather's quite good here in Edinburgh. Well, good for Edinburgh. And then I'll start lecturing again at 2. So I'll put that up on a slide. But it's a practical session now till 1 p.m. British summer time, local time here, 2 p.m. in mainland Europe. Then so that's in most of mainland Europe. Apologies if you're Portuguese. And then we'll, so practical session till 1, and then lunch 1 till 2, and then I'll start lecture again at 2, when I'll talk about slightly more esoteric features which are still useful, called virtual topologies, which allow you, and derived data types, both of which are actually very useful in terms of moving to the next level of MPI programming, not just using MPI conworld and sending and receiving integers, but sending and receiving more complicated objects like structures or array subsections, and also managing communicators such that you can arrange them into topologies, grids, and cubes and such like, which is a useful technique.